So we left off part one talking about the black body curve, and it's basically a constant that astronomers have come up to realize that anything, again, that has mass is considered a black body. Anything that can take heat and bounce it back out again is a black body. So astronomers only need to measure apparent brightness in as few as two measurements because it makes the same curve everywhere you go. So line B, for example, is visible light. It peaks. It's actually a little bit higher if you look at the blue than it is at the yellow. So it gives a little more blue light. Actually, line A gives a lot more blue light. That's a blue giant. So line B, they look about equal, actually, but there is more blue. Line C shows more yellow than blue. That would make it a yellow like our sun. So star A is Rigel. Yes, it's a super giant. It's a blue giant rather. It's 30,000 Kelvin. That's hot. So it gives off more blue than yellow. And obviously, if you look at the sky and you see Rigel, the upper shoulder of Orion, it's blue. It's white blue. Star C is more like Betelgeuse. It has a lot more red than blue. And opposite of Rigel up in Orion, down to the foot, is the red supergiant Betelgeuse, and it's pretty dark red. It almost looks like Mars. Okay, so apparent magnitude is the brightness an object appears to be from here on Earth. Kind of like if you set yourself out, whether you're using a telescope or naked eye, they still appear to be brighter. Okay, a ground-based telescope, they appear to be brighter based upon their proximity. So, some stars are a lot further away and might be brighter, but that's kind of like some bright headlights 10 miles down the road compared to a flashlight 10 feet away. That flashlight's going to look a lot, it's going to appear a lot brighter. So the apparent magnitude of a flashlight 10 feet away is going to be much more bright than the car's headlights 10 miles away. Okay, so with stellar colors and temperatures, again, the if it's blue, it's going to be really, really hot. Electric blue, they say for 30,000. That's bright blue. It's a bright, bright white blue. So Rigel is a pretty light blue, actually. Vega and Sirius the dog star, it says its temperature is 10,000. Its color is white. But if you look at it, it's very bright. It's one of our brightest ones we see for the naked eye. And it twinkles so strongly in the red, blue, it looks like an airplane that just stuck up in a holding pattern. Canopus is yellow. Our sun and Alpha Centauri are both yellow. Obviously, if you look at our sun, it looks yellow. Just don't stare at it. And of course, the red giants, Arcturus, Aldebaran, Betelgeuse, and Barnard star are red. Okay, so spectral classification. Wow. O, B, A, F, G, K, M. They are arranged in that order now based upon temperature. That's not how they originally classified. Originally, they classified them A through at least O, A, B, and then they compiled things together and they rearranged and they kept the same old ABO format and didn't make a new format. So now the way to remember the order is to say, oh, be a fine guy, kiss me, or be a fine girl, kiss me. So O is the hottest, M is the coolest. So it was originally based upon the hydrogen spectral line intensities, thinking that some stars had more hydrogen than others. So A stars had the most, B had the second most, all the way to P. Yeah, so P had the least. And with more understanding of the hydrogen spectra, they realized they made a mistake. The letter classification remains, but only the letters, again, O, B, A, F, G, K, M, remain. So there's a little history, but basic classification is based upon the stellar surface temperature. So classification of stars is based upon the surface temperature, not the spectral lines anymore. O the hottest, M the coolest. There's a nice little table straight out of your textbook. O being 30,000, clear down to M being 3,000. All right, stellar sizes. I would love for you to click on this YouTube example up here. It's a short little YouTube. You've probably seen it all through elementary school and middle school. But it's really cool comparing the sizes of stars rather, our sun to other stars as they come by. And it really puts things in perspective. I like it. So red dwarf is about 8/100ths the size mass of our sun. Our sun is one solar mass. Guess what the mass is based upon? Our sun. A red giant can be 5 or more. Okay, that should be greater than. So greater than 5 solar masses. And blue and white supergiants, those guys can be 150 times the size of our sun, mass-wise. Not diameter, just mass. Diameter varies greatly. All right, so we got this thing called a Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram put together by these guys, Hertzsprung and Russell. What a coincidence. It has for its y-axis the luminosity in solar units. So luminosity is measured in solar units. That is how bright it is compared to our sun. So therefore our sun would have a luminosity of 1. Rigel up there 10,000 times brighter than our sun, more luminous. And then it goes down to like Proxima Centauri, 0.0001 1/10,000th as much as our sun. That's not too bright. Across the bottom is our wonderful old surface temperature, OBAFGKM. And that is 30,000, 10,000, 6,000 to 3,000. It's basically 30,000 down to 3,000. It's good to know and diagram this. There's a third axis that goes from the right side and cuts across, slices from 3,000 up 3,000 temperature up to 10,000 luminosity. Slices that way, and that will be discussed. Okay, not here. Anyway, I'll get to it. So when you plot these now, you can see that the supergiants, Rigel, Vega, they're all over here in the hot blue and hot side, big. Betelgeuse and the red supergiants on the right side, cool, but also very big, very luminous. You can take a light bulb that's not a whole lot of wattage, but make it really big, and it's pretty bright. It's pretty luminous. Whereas you can take a really high-powered little LED light that's small, but make it very luminous. It can be small, but very luminous because it's very hot, maybe. The main sequence stars, you can see there's like a little curve going through there. That's called the main sequence. Our sun is smack dab in the middle. It's really a yellow dwarf star. It's not huge. It's part of the main sequence. The main sequence is those stars which are in their main burning sequence. They're in their regular, what you call lifetime of the stars, are still burning helium or fusing helium to make hydrogen, fusing hydrogen to make the helium. So that's still going on at a regular rate or whatever rate it is based upon the mass and the temperature. But all that is cooking as normal. You have a white dwarf, very small but very hot still. And on the right side, which is missing, is the brown dwarfs, little dying cool stars. So here's our diagram again, better diagram. The brown dwarfs would be over there. The main sequence flows right through the middle. And the blue giants are on the top left, very hot and bright. So the main sequence equilibrium our main sequence stars are in, such as our sun, is basically an equilibrium between the outward acting force of the force of temperature from all the fusion going on and the inward acting force of gravity. So all that mass is pulling it in, but the nuclear reaction going on in the core is forcing a lot of heat and radiation out, and it keeps it there in a stable area. That's a little fuzzed, a little big, but boom, there we go. So red dwarfs, such as Barnard star, it's a red dwarf. I put brown dwarfs in the other one. They're in that lower region. White dwarfs, main sequence stars right down the middle. This diagram does not have the supergiants on it, but that's okay. Binary stars, pretty cool thing. Binary stars are two stars that orbit each other, kind of like in Star Wars. You look at, he's got two stars rising over the planet. I guess that could work if they're far enough away. They, in theory, have to be a lot further away than our sun, because if our sun was one of two stars eclipsing each other, we'd probably be a lot hotter than we would. And when they eclipsed, if they eclipsed each other on their same plane, which would you'd think they would, temperature would vary greatly. Anyway, binary stars are two stars orbiting each other. So if the observer is in the same plane as the binary stars, when they eclipse each other, they'll look dimmer. When they're side by side, they look a lot brighter. If one star is brighter than the other, then you'll be able to definitely tell another third brightness. From the spectral analysis, they can look and see that you can see the starlight is blue shifted, it's red shifted, which means it's moving away and away from you and to you. So that does mean it's moving. If it's moving away and to you at the same time from period to period, that means it's making a big circle. So it's eclipsing another star. That's a lot how we find out eclipsing binaries, because they're so far away. We got to look at the redshift, blue shift. All right, a star has a certain lifetime. What is that? Well, 3 to 5 billion years for our sun. So our sun, they say in about 3 billion years, not million, but billion years, it'll eventually fizzle out. It'll go. So the rapid rate of nuclear burning deep inside a star releases tons of energy. How long can the fire continue to burn? We can estimate a star's lifetime by dividing the amount of fuel available, the mass of the star, by the rate at which the fuel is burning. Our star is a yellow star. It's not burning it that hot, that fast. Its rate, because it's cool, compared to Rigel, which is blue, burning a lot faster. So the mass divided by luminosity, the brightness. Luminosity is 4 times pi times another constant times the radius squared times temperature to the fourth. That's a lot of stuff. So if you use solar units where L is measured in solar luminosities, it's a lot easier. We can just say luminosity is equal to the radius squared times temperature to the fourth. The average temperature of the photosphere of our sun is 5,800 Kelvin. So what is the luminosity of a star having 3 times the radius of our sun and a temperature of about 10,000 K? You can plug this in, and it's about 1.7 times hotter than our sun's photosphere. So we put that in place of T, plug it in to that big equation, and we find out it's 79 times more, almost 80 times more luminous or brighter than our sun. That's pretty stinking bright. I think we'll end part 2 notes about here, and I'll pick up from there.